Hello everybody, my name is Jess and I will be discussing optimization and curve fitting. So to start with, for the motivation, root location and optimization are related in the sense that both involve guessing and searching for a point on a function. Their main difference is that root location involves searching for zeros of a function or functions, while optimization involves searching for either minimum or maximum. So this figure depicts on what I said earlier. For the optimum is the point where the curve is flat. In mathematical terms, it corresponds to the value of x, where the derivative of the first derivative is equal to 0. And the second derivative indicates that whether the optimum is a minimum or a maxima. So if um, the second derivative is greater than 0, then the point is a minimum. And if it is less than 0, then the point is maximum. Understanding the relationships between roots and optima would suggest a possible strategy to finding the latter. Some optimization methods seek to find an optima by solving the root problem, that is, the first derivative is equal to 0. And it should be noted that such searches are often complicated because the first derivative is not always available analytically. Thus, one must sometimes use a finite difference approximations to estimate the derivative. Beyond viewing optimization as a roots problem, it should be noted that the task of locating optima is aided by some extra mathematical structure that is not part of root finding. This tends to make optimization a more tractable task, particularly for multi-dimensional cases. In history, we all know that differential equation methods are used to determine the optimum solution. Bernoulli, Euler, Lagrange, and others laid the foundation of calculus variations, which deals with minimization of the function. Lagrange multiplier method was developed to optimize constraints problem. That is, optimization problem where the variables are bounded in some way. The development or the first major development in numerical approach was after World War II when the development of the digital computers. Koopmans and Kantorowicz independently work on the general problems of least cost distribution of supplies and products. Koopman student Danzig in 1947 invented the simplex procedure for solving linear programming problems, and this approach paved the way for other methods constrained optimization to be developed by a number of investigators. Notable are Charles and his co-workers. So unconstrained optimization approach developed rapidly right after the widespread availability of the computers. So these are some common problems or examples of optimization in engineering field. Optimization and engineering practice, so most of the time they are of descriptive models. Descriptive models are derived to stimulate the behavior of engineering device or system. In contrast, optimization typically deals with finding the best result or optimum solution to a problem. So in the context of modeling, they are often termed prescriptive models, since they can prescribe, of course, or they can prescribe a course of action or the best design. And engineers must continuously design devices or products that perform tasks in an efficient fashion. However, there are constraints or limitations by the physical world. And one of those is, or furthermore, they must cut, they must cut down the costs. So they are always confronting optimization problems that balance performance and limitation. So these are the common problems in optimization in the field of engineering. So to name a few, designing an aircraft for minimum weight and maximum strength. And another one would be the inventory control, and another is design waste treatment system to meet water quality standards of least cost. So these are just some common examples of optimization problems in engineering. Optimization for a parachute. So here is the problem statement. This is a sample problem. So the problem statement is that you are an engineer working for an agency planning to lift air to airlift supply to refugees in a war zone. The supplies will be dropped at low altitude, around 500 meters, so that the drop is not detected and the supplies fall as close as possible to the refugee camp. The chutes open immediately upon leaving the plane. To reduce damage, the vertical velocity on impact must be below a critical value of 20 meters per second. The parachute used for the drop is depicted or is shown on the figure. The cross-sectional area of the chute is that of half of a sphere, and that is A is equal to 2 pi r squared. The length of each of the 16 cords connecting to the chute to the mass is related to the chute's radius by length is equal to the square root of 2r. So, and we know that the drag force for the chute is a linear function of its cross-sectional area, and that is C is equal to Kc times A, where C is the drag coefficient, Kc is the proportionality constant parameterizing the effect of area on drag, and A is the area. Also, you can divide the payload into many parcels as you like, and that is the mass of each individual parcel can be calculated by m is equal to mt over n, where m is the mass of an individual parcel, mt is the total load being dropped, and n is the number of parcels. Finally, the cost of each chute is related to chute size in a nonlinear fashion, and that is cost per chute is equal to C naught plus C1L plus C2A squared, where C naught, C1, and C2 are cost coefficients. The constant term C naught is the base price for the chute. The nonlinear relationship between cost and area exists because larger chutes are much more difficult to construct than small chutes. And the question is, determine the size R and the number of chutes N that result in a minimum cost while at the same time meeting the requirement of having a sufficiently small impact velocity. So this is the solution. The object here is to determine the number of size of parachutes to minimize their cost, and the problem is constrained because the parcel must have an impact velocity less than the critical value. So the cost can be computed by multiplying the cost of the individual parachute by the number of parachutes n. And the function you wish to minimize, which is formally called the objective function, is written as minimize C is equal to n quantity C naught plus C1 times L plus C2 area squared. So where C is the cost in dollars, A and L are calculated via the previous equations. So next, we must specify the constraints. So for this problem, we have two constraints. The first is the impact velocity, which must be equal or less than the critical velocity. And second is the number of parcel. It must be an integer and greater than or equal to 1. So at this point, the optimization problem has been formulated. So as can be seen, it is a nonlinear constraint problem. Although the problem has been broadly formulated, one more issue is that, or that needs to be addressed, is how do we determine the impact velocity, v? So recalling in chapter 1 that the velocity is just, or the velocity of a falling object is just equal to v gm over c. V is equal to gm over c quantity here. So v is equal to gm over c quantity 1 minus e to the power of quantity c over m times t. So with this formula, we know that v is the velocity, that is meter per second, g is the acceleration due to gravity, m is the mass, and t is the time. So although this equation provides the relationship between the velocity and time, but we need to know how long the mass falls. So therefore, we need the relationship between the drop distance z and the time of the fall t. So the drop distance can be calculated using the equation given, or here, this equation. It is through integration. So integrating this equation, we have z is equal to the integral of gm over c, quantity 1 minus e to the power of negative quantity c over m times t dt from 0 to t. So this integral, this will result to this equation. That's 4.9. So that is equal to z is equal to z naught minus gm over c plus gm squared over c squared, quantity 1 minus e to the power of c and quantity t. So where we know that c naught is the initial height and initial height. So as plotted in figure 4.3. So this way, it can provide to predict z given the knowledge of t. However, we do not need z as a function of time to solve the problem. Rather, we need to compute the time required for the parcel to fall the distance z naught. Thus, we recognize that we must reformulate this equation. So as a root finding problem. So using that, we can derive, we must solve for that time which z goes to 0. So this one, so function of time is equal to, when z is equal to 0, so this gives us z naught minus gm over c times t plus gm squared over c squared quantity 1 minus e to the power of quantity c over m times t. So once the time to impact is computed, we can substitute this equation to our first equation to solve for the impact velocity. And the final specifications of a problem therefore would be minimize c is equal to n quantity c naught plus c1l plus c2a squared l. So we know that, so these are our constraints. So the velocity must be less than the, this again, this is the critical velocity. Yeah, the impact of, so this is our constraint. The impact velocity is must be less than the critical value. So this one, these are our constraints, and shoots must be greater than or equal to one other integer, where a is equal to 2 pi r squared, l is equal to square root of 2r, c is equal to kca, and we have the value of m, that's mt over n, and we also have the value of t. But we will solve this problem in example 15.4. That is in chapter 15. But for the time being, we recognize that it has most of the fundamental elements of other optimization problems that routinely confront in engineering practice. And these are the problems will involve an objective function that embodies our goal. Second is there will be a number of design variables. These variables can be real numbers or they can be integers. In our example, these are R for the real and N for the integers. And the problem will also include the constraints that reflect the limitation that we are working under. So we should make one more point before proceeding. Although the objective function and constraints may superficially appear to be simple based on the equation, but they may in fact be the tip of the iceberg. And that is there may be an underlying complex dependencies and models. So for instance, as in our example, they may involve other numerical methods. This means that the functional relationship that you will be using could actually represent large and complicated calculations. Thus, techniques that can be or that can find the optimal solution while minimizing function evaluations can be extremely valuable. So for the mathematical background, there are a number of mathematical concepts and operations that underlie optimization because we believe that they will be more relevant to us in this context, then but we will defer the discussion on specific mathematical prerequisites until they are needed. So for example, we will be discussing the important concepts of gradient and Hessians at the beginning of chapter 14 on the multivariate general topic of how optimization problems are classified. So, an optimization or mathematical programming problem can be generally stated as finding x which minimizes or maximizes the function of x that is subject to these di x that is less than or equal to ai, where I is equal to 1, 2, and so on. And the other is e to the ix is equal to bi. Again, I is equal to 1, 2, and so on, where x is the dimensional vector. Fx is the objective function, dix are inequality constraints, and ei of x are equality constraints, and ai and bi are constants. So optimization problem can be classified on the basis of the form of f of x. So if f of x and constraints are linear, then we have linear programming. If f of x is quadratic and the constraints are linear, then we have quadratic programming. And if f of x is not linear or quadratic and or of constraint are and or the constraints are non-linear, then we have non-linear programming. So further, with the previous equations are included, then we have the constraint optimization problem. Otherwise, it is unconstrained optimization problem. It is good to note that the constraint problems, the degrees of freedom are given by n minus p minus m. So generally, the optimum solution P plus M must be less than or equal to N. So if P plus M is greater than N, then the problem is said to be over-constrained. So another way in which optimization problems are classified is by dimensionality. So this is not, or this is most commonly done by dividing them into one-dimensional and multidimensional problems. As the name implies, one-dimensional problems involve functions that depend on a single dependent variable. So here in the picture, you can see this here. A is a one-dimensional optimization. So this figure illustrates how minimization of f of x is equivalent to the maximization of negative f of x. And this one is a two-dimensional optimization. It is good to note that this figure can be taken to represent either a maximization that's the contours are increasing in elevation up to the maximum like a mountain, or a minimization that's the contours decrease in elevation down to the minimum like a valley. So this figure, the search then consists of climbing and descending of one-dimensional peaks and valleys. So multidimensional problems involve functions that depends on two or more dependent variables. So in the same spirit, a two-dimensional optimization can again be visualized as searching out peaks and valleys, just like here in figure B. However, just as in real hiking, we are not constrained to walk in a single direction. Instead, the topography is examined to efficiently reach the goal. So finally, the process of finding maximum versus the finding of minimum is essentially identical because the same value x asterisk both minimizes the function x, function of x, and maximizes the negative function of x. So this equivalence is illustrated or graphically seen in the picture. That's letter A. All right, so these are the one-dimensional unconstrained optimization. So as of the moment, I will be explaining the golden section search and the parabolic interpolation. And my co-reporter will be explaining the Newton's method and Brand's method. So let's start. So before we start with the golden search section, just to give you a heads up that this chapter will describe the technique to finding the minimum or maximum of a function of a single variable f of x. So a useful image that can be seen at the bottom is, or a useful image in this regard is the one-dimensional roller coaster like a function that can be seen at the bottom here. So the root location implies that the root location is complicated by the fact that several roots can be can occur for a single function. So similarly, both local and global optima can occur in optimization. Such cases are called the multimodal. In most all instances, we will be interested in finding the absolute highest or lowest value of function. Thus, we must take care that make mistake, we do not mistake a local result to a global optimum. So distinguishing a global from a local extremum can be very difficult problem for general case. So there are three usual ways to approach this problem. So first is insight into the behavior of low-dimensional functions can sometimes be obtained graphically. Second, it may be possible to find optima based on wildly varying and perhaps randomly generating starting guesses. And then select the largest of these global. Then the third, or finally, we will perturb the starting point associated with a local optimum and see if the routine returns a better point or always returns to the same point. Although these approaches can have utility, the fact is that in some problems, usually the large ones, there may be no practical way to ensure that you have located a global optimum. However, although you should always be sensitive to the issue, it is fortunate that there are numerous engineering problems where you can locate the global optimum in an ambiguous fashion. Just as in root location, optimization in one dimension can be divided into bracketing and open methods. Golden section search is an example of a bracketing method that depends on initial guesses that bracket a single optimum. This is followed by an alternative approach, that is the parabolic interpolation, which often converges faster than the golden section search, but sometimes diverges. And another method described in this chapter is an open method based on an idea from calculus that the minimum or maximum can be found by solving f prime x that is equal to 0. So this reduces the optimization problem to finding the root of f prime of x using techniques of the sort described in part 2. And we will demonstrate one version of this approach, that is the Newton's method. Finally, an advanced hybrid approach that is called Brent's method. This approach combines the reliability of the golden section search with the speed of the parabolic interpolation. So now we'll discuss the golden section search. So in solving for the root of a single nonlinear equation, the goal was to find the value of the variable x that yields a non-zero of function f of x. So the single variable optimization has the goal of finding the value of x that yields an extremum, either a minimum or a maximum, of the function of x. So the golden section search is a simple general purpose single variable search technique. So it is a similar approach to bisection for locating the roots that we can see in chapter 5. So recall that bisection hinged on defining an interval specified by lower guess xl and an upper guess xu that bracketed a single root. The presence of a root between these bounds was verified by determining that fxl and fxu had different signs. So the root was then estimated at the midpoint of the interval, that is equal to xr is equal to xl plus xu over 2. So the final step of the bisection iteration involved determining a new smaller bracket, and this was done by replacing whichever of the bounds xl or xu had a function value with the same sign as fxr. One advantage of this approach was that the new value xr replaced one of the old bounds. So now we can develop a similar approach for locating the optimum of a one-dimensional function. So for simplicity, we will focus on the problem of finding a maximum. When we discuss the computer algorithm, we will describe a minor modification needed to simulate a minimum. So, as with bisection, we can start by defining an interval that contains a single answer. That is, the interval should contain a single maximum. That's why it's called unimodal. And we can adopt the same nomenclature for a bisection, where xl and xu defined as the lower and the upper limit of the interval. However, in contrast to bisection, we need a new strategy to finding a maximum within the interval. Rather than using only two function values, which are sufficient to detect the sign change and 0, we would need three function values to detect whether a maximum occurred. Thus, thus, an additional point within the interval has to be chosen. So next is we have to pick the fourth point. Then the test for the maximum could be applied to discern whether the maximum occurred within the first three or the last 3 points. The key to making this approach efficient is the wise choice of the intermediate points. So as in bisection, the goal is to minimize function evaluations by replacing old values with new values. So the goal can be achieved by specifying the following two conditions. So L naught is equal to L1 plus L2, and we have the proportion of L1 over L2 is equal to L2 over L1. So in the picture shown, this is the initial step of the golden section search algorithm that involves choosing two interior points according to the golden ratio. So the first condition, that is the L0 is equal to L1 plus L2, is the sum of the two sublengths. So the original length is L0 and its sublength is L1 plus L2. The second says that the ratios of the length must be equal. So the first equation can be substituted on the second equation, and this will give us this result. That is L1 over L1 plus L2 is equal to L2 over L1. So if the reciprocal is taken, let's say R is equal to L2 over L1, then we arrive with this equation that's 1 plus R is equal to 1 over R. Or R squared plus 1 is equal to 0, which can be solved for the positive roots of 0.61803. So this value, which has been known since the antiquity, is called the golden ratio. So because it allows optima to be found efficiently. It is the key element of the golden section method we have been developing conceptually. Let us now derive an algorithm to implement this approach on the computer. As shown in the figure 13.4, the method starts with two initial guesses, xl and x2, that bracket one local extremum of f of x. Next, two interior points x1 and x2 are chosen according to the golden ratio. So that is r is equal to square root of 5 minus 1 over 2 quantity xu minus xl. And x1 is equal to xl plus d, and x is equal to xu minus d. The function is evaluated at these two interior points. Two results can occur. So if fx1 is greater than fx2, then the domain of x to the left of x2 from x1 to x2 can be eliminated because it does not contain the maximum. So for this case, x2 becomes the new xl for the next iteration. Second, if fx2 is greater than fx1, then the domain of x to the right of x1 from x1 to xu would be eliminated. In this case, x1 becomes the new xu for the next iteration. Now, here is the real benefit from the use of the golden ratio. Because the original x1 and x2 were chosen using the golden ratio, we do not have to recalculate the function values for the next iteration. For example, for the case earlier, the old x1 becomes the new x2. This means that we already have the value for the new fx2 since it is the same as the function value at the old x1. So to complete the algorithm, we now only need to determine the new x1. This is done with the same proportionality as before. So x1 is equal to xl plus d. So this formula here is d. So a similar approach would be used for the alternate case where the optimum fell in the left subinterval. As the iterations are repeated, the interval containing the extremum is reduced rapidly. In fact, each round, the interval is reduced by a factor of the golden ratio that's about 61.8%. That means that after 10 rounds, the interval is shrunk to about 0.61810 or 0.008 or 0.8% of its initial length. So after 20 rounds, then it is reduced to 0.0066%. This is not quite as good as the reduction achieved with bisection, but this is a harder problem. So an example for golden section search. Use the golden section search to find the maximum of fx is equal to 2 sine x minus x squared over 10, with the interval xl is equal to 0 and xu is equal to 4. So first, the golden ratio is used to create the two interior points. So d is equal to square root of 5 minus 1 over 2 quantity xu minus x0, which is equal to 2.472. Then we have the two interior points x1, that is, this is xl plus d. So this becomes 2.472. And for the x2, xu minus d, or 4, that is equal to 4 minus 2.472, which is equal to 1.528. So the function can be evaluated at the interior points. So fx2 is equal to, the value of f of x2 is 1.528. So this becomes 2 sine, or substitute the value of x to the equation. That is 2 sine 1.528 minus 1.528 squared over 10, which is equal to 1.765. And fx1 is equal to the value of x1, which is 1.52, which gives us 0.63. So we can see here that x2 is greater than x1. So the maximum is in the interval defined by xl, x2, and x1. Thus, for the new interval, the lower bound remains to be 0, or xl is equal to 0, and x1 becomes the upper bound. So x1 becomes xu, which is equal to 2.472. In addition, the former x2 value becomes the new x1. That is, x1 becomes 5 point, or x1 becomes 1.528. Further, we do not have to recalculate fx1 because it was determined on the previous iteration, which is equal to 1.765. So all that remains is to compute the new values of d and x2. So computing the values, we have now the value of, since we have new xu, which is the former x1, then our new value for d is equal to 1.528. And our x2 becomes 0.944. So this is the table if we perform uh, the operation, or if we perform 8 iterations. So the function at x2 is f 0.994 is equal to 1.531. The function evaluation at x2 is 1.531. Since this value is less than the function at x1, then the maximum is in the interval prescribed by x2, x1, and xu. So the process can be repeated. So this is the result of the iterations. It is good to note that the current maximum is highlighted for every iteration. So these are the maximums. After the 8th iteration, the maximum occurs at x is equal to 1.4427 with a function value of 1.7755. Thus, the result is converging on the true value of 1.7757 at x is equal to 1.4276. Recall that for bisection, an exact upper bound for the error can be calculated at each iteration. Using similar reasoning, an upper bound for golden section search can be derived as follows. So once an iteration is complete, the optimum will either fall in one of the two intervals. If x2 is the optimum function value, it will be in the lower interval. That's xl, x2, and x1. If x1 is the optimum function value, it will be the upper interval. That's x2, x1, and xu, because the interior points are symmetrical. Either case can be used to define the error. Looking at the upper interval, if the true value were at the far left, the maximum distance from the estimate would be change of xa is equal to x1 minus x2, or, and substitute the values for x1 and x2. So we have xl plus r quantity xu minus l minus xu plus rxu minus xl. So this will give us the result of 0.236 xu minus xl. So if the true value at the far right, then the maximum distance from the estimate would be 0.382 quantity xu minus xl. So therefore, this case would represent the maximum error. This result can be normalized to the optimal value for the iteration x up to yield EA epsilon A is equal to 1 minus R absolute value of xu minus xl over x up times 100. So this estimate provides a basis for terminating the iteration. So this is the pseudocode for the golden section search algorithm for maximization. So the minor modification to convert the algorithm to minimization is or can be seen in B. So this one. So these are just the modification. In both versions, the x value for the optimum is returned as the function value gold. In addition, the value of f of x at the optimum is returned as the variable f x. So you may be wondering why we have stressed the reduced function evaluations of the golden section search. Of course, for solving a single optimization, the speed savings would be negligible. However, there are two important contexts where minimizing the number of function evaluations can be important. And these are many evaluations. So in many evaluations, there are cases where the golden section search algorithm may be a part of a much larger calculation. In such cases, it may be called many times. Therefore, keeping function evaluation to a minimum could pay great dividends for such cases. Next is it is time-consuming evaluation. For pedagogical reasons, we use simple functions in most of our examples. You should understand that the function can be very complex and time-consuming to evaluate. So, for example, in the later part of this book, we will describe how optimization can be used to estimate the parameters of a model consisting of a system of differential equations. For such cases, the function involves time-consuming model integration. Any method that minimizes such evaluations would be advantageous. Next is the parabolic interpolation. So parabolic interpolation takes advantage of the fact that a second-order polynomial often provides a good approximation to the shape of f of x near the optimum, as can be seen in the picture. Just as there is only one straight line connecting two points, there is only one quadratic polynomial or parabola connecting 3 points. Thus, if we have 3 points that jointly bracket an optimum, we can fit a parabola to the points. Then we can differentiate the quadratic equation or the quadratic polynomial, set the result equal to 0, and solve for an estimate of the optimal x. It can be shown through some algebraic manipulation. But the result is this. So x3 is equal to fxo, quantity x1 squared minus x2 squared plus fx1, quantity x2 squared minus x0 squared plus fx2 times or quantity x0 squared minus x1 squared over 2fx0, quantity x1 minus x2 plus 2fx, quantity x2 minus x1 plus 2fx, x0 minus f1. So for this equation, x0, x1, and x3 are the initial guesses. Or rather, x0, x1, and x2 are the initial guesses. So x3 is the value of x that corresponds to the maximum value of the parabolic fit to the guesses. After generating the new point, there are two strategies for selecting the points for the next iteration. The simplest approach, which is similar to the second method, is to merely assign the new points sequentially. That is, for the new iteration, C0 is equal to C1, Z1 is equal to Z2, and Z2 is equal to Z3. Alternatively, as illustrated in the following example, a bracketing approach similar to bisection or Gaussian section search can be employed. We should mention that just like the false position method, parabolic interpolation can get hung up with just one end of the interval converging. So thus, convergence can be slow. So for example, notice in our example that will be displayed later, 1.00 was an endpoint for most of the iterations. So this method, as well as the others using third polynomials, can be formulated into algorithms that contain convergence tests. Careful selection strategies for the point to retain on each iteration and attempts to minimize round-off error accumulation. So this is an example. The same example, but this time use parabolic interpolation to approximate the same equation or function with initial guesses x0, x0 is equal to 0, x1 is equal to 1, x2 is equal to 4. So the solution is to get the function values. So f x0 is equal to 0, so substituting 0 to the function, so we'll have f of 0 is equal to 0, fx1 is equal to 1.5829, and fx2 is equal to negative 3.11, 36, and substitute this to the equation earlier to get x3. So substitute the values. We all have the values here, x0, x1, and x2, as well as the function. So substituting all the values, we will have the value of x3, which is equal to 1.5055. So getting the function value, substituting 1.5055 to the equation, this will give us 1.7691. Next, a strategy similar to the golden section search can be employed to determine which point should be disregarded. So because the function value of the new point is higher than the intermediate point, and the new x value is to the right of the intermediate point, the lower guess x0 is discarded. Therefore, for the next iteration, we will have these values. So on the first iteration, we have x0 is equal to 0. So on the next iteration, we disregarded the x0 and replaced it with x1. Therefore, for the next iteration, we have x0 is equal to 1, x1 is equal to 1.5055, and x2 is equal to 4. So getting their function values, fx0 is equal to 1.5829, fx1 is equal to 1.7691, and fx2 is equal to negative 3.1136. So substitute these values to the equation. So we have a new value of x3, which is equal to 1.4903. So getting the function value, we have f quantity 1.4903 is equal to 1.7714. So the process then be repeated. So this is the tabulated form for the process. Thus, within the 5 iterations, the result is converging rapidly on the value of 1.7757 at x is equal to 1.4276. And that ends my report. Thank you very much for listening, and have a